Hello everyone, in this video I will share with you how to use MATLAB apps to do signal processing. First of all, I will briefly introduce some signal processing apps provided by MATLAB, then show you how to use these apps to do signal processing through a demo called Preprocessing and Analyzing an Electrocardiogram, the ECG signal. And last, there's a summary. Signal processing involves all aspects of our life, such as biomedicine, communication electronics, computer vision, and so on. Usually, we need to load or import the signal before we do signal processing. MATLAB supports signals represented by vectors, matrices, timetables, and time series. Then, the signal is pre-processed and is observed and analyzed by time-frequency analysis. Generally, the pre-processing includes filtering, smoothing, resampling, detrending, and calculating envelope. The two steps, including pre-processing and exploration of signals, iterate with each other until the analysis meets our needs. Finally, the signals are labeled for further feature extraction and machine learning purposes. All the results of the analysis and the pre-processing are shared with others. Next, we will use a demo to show how to use MATLAB apps for signal analysis and pre-processing. Let's try it with MATLAB. MATLAB provides a series of interactive apps with user interface to facilitate more convenient use by users. These apps involve all MATLAB application fields, such as math, statistics and optimization, machine learning, and deep learning. The apps we are going to learn are about signal processing, which are under the label of signal processing and communications. The most basic Signal Analyzer app provides a tool to visualize, measure, analyze, and compare signals in time and frequency domains. The most commonly used are Filter Builder and Filter Designer apps. Through them, we can easily design and analyze digital filters by pulling down menus and filling parameters. For wavelet analysis, MATLAB provides the Wavelet Signal Denoiser app to use Descriptive wavelet transform to denoise signals, and provides the Signal Multiresolution Analyzer app to analyze and visualize signals with multi-resolution analysis. Let's first load and plot the electrocardiogram, the ECG signal, which is the electronic signal generated by heartbeats. It's widely used to reveal the health of the heart, such as whether there's an arrhythmia, infection, tachycardia, and other diseases. We can see here ECG denotes the amplitude of the signal, Fs is the sampling rate, and T is the time variable. Next, we open the Signal Analyzer by using this command line or by click on the icons of the app. We drag the ECG signal into the displaying panel and add its time information as time t here. Let's check the frequency spectrum of the signal. We can see there's a large interference at around 60 Hz. In order to remove the interference, we need to use a bandstop filter. There are several pre-processing options provided by the app, like smooth, low pass, high pass, and so on. We also can add our custom function here. In this example, we use a bandstop filter. We enter the lower passband frequency at 59 Hz and upper passband frequency at 61 Hz. Then we check on the bandstop. It mentions that the signal will be overwritten. So in order to keep the original signal, we make a copy of the ECG signal and renamed it as ECG filtered. We add one more display in order to compare the two signals. Then we click on the band-stop. We can see the interference has been removed. And next, we want to remove the trend of the signal by using the detrend function provided by the app. We can see the linear trend of the signal has been removed. We export the signal into our workspace. However, the slow variant caused by movement and heartbeats is still there. How to remove this kind of trend? Wavelet transform provides us an effective tool to do this. Wavelet transform has been widely used in various engineering fields such as speech signal processing, medical signal processing, image processing, and so on. What's descriptive wavelet transform? The basic idea is to decompose the signal into a high-frequency signal, also known as a detailed signal, and a low-frequency signal, also known as a approximation signal. The approximation signal continues to be decomposed into a detailed signal and approximation signal through a high-pass filter and a low-pass filter respectively. This process continues until the signal is decomposed into several subband signals. For example, if we set the level as 4 and the sampling frequency as 1000 Hz, that is to say, the signal with the next frequency equals 500 Hz. It is decomposed into 4 levels of the detailed signal and the approximation signal. The frequency of each subband is shown in this figure. The principle of signal detrending based on descriptive wavelet transform is shown in this figure. First, we use descriptive wavelet transform to decompose the input signal into some subband signals, some of which represent the trend of the signal. We can set the coefficients of this subband to 0 and then reconstruct the signal through the inverse descriptive wavelet transform. And this time, the subband signal representing the trend has been removed. Let's look at how to use the Signal Multiresolution Analyzer app to detrend the ECG signal. We can open Signal Multiresolution Analyzer app by using this command line or by click on the icons of the app. We load the ECG filtered signal into the app. By default, Sim4 wavelet has been used, and the decomposition level equals 4. This table here shows the frequencies of each subband and also the relative energy of each subband. From the figures here, we can see none of the subband can be used to represent the trend of the signal. So we further increase the decomposition level to 10, for example. More decomposition level, the narrower the subband. Now we can see the approximation subband can be used to represent the trend of the signal. So we reconstruct the signals by including all the subband except the approximation subband. The blue line here shows the reconstructed signal. We can see the trend of the signal has been removed. Now we can export the reconstructed signal into our workspace, and we can generate a MATLAB script for further use. To recap what we have done, first we used the Signal Analyzer app to import, visualize, analyze, and pre-process the ECG signal. Here, the pre-processing includes filtering and detrending. Next, we use the Signal Multiresolution Analyzer app to perform multi-resolution analysis. Through multi-resolution analysis, the low-frequency component representing the signal trend have been removed. To sum up, the signal processing apps in MATLAB provide us tools with more friendly user interfaces. They make us more convenient to do signal analysis and pre-processing tasks. The users who are not familiar with MATLAB commands can carry out relative work more quickly. Graphic user interfaces provide us a more convenient way to adjust the parameters of different algorithms. I hope now you know more about how to use MATLAB apps to do signal processing. If you need more information, please check out the documentation and other resources in the description below. Thank you.